Hello there. So today we're going to be talking about permutations with repetitions and something called circular permutations. Again, this is still combinatorics. We're still figuring out how many ways something can occur. And so to start off with, I have a warm-up problem for us to look at. If we look at the letters in the word trip and the word pool, if we were to list out all the distinguishable arrangements of those letters, it would take us a while. But if we look at TRIP, we could also write this as TRPI. That's a different arrangement of the letters. Okay, you could still have TIRP and TIPR. Okay, and then you could still go TPIR or TPRI. So even just starting with the letter T, you've got 6 different arrangements for those letters. And then you would start with the letter R, you would have 6 more. If you started with the letter I, you'd have 6 more. And you start with the letter P, you'd have 6 more. So all told, there are 24 different arrangements. To save time, I'm not going to do all that. If you think about it in terms of the fundamental counting principle, you would have 4 options for the first letter, 3 options for the second letter, 2 options for the third letter, and then 1 option for the fourth letter. So 4 times 3 times 2 times 1 is where we get the 24. What's different about the word pool is the fact that we have the same letter twice. So for us to distinguish between POOL like this, or if we were to switch the O's around, well, we'd still have POOL. Okay, and that's not distinguishable, even though we technically, you could say that I switched the O's around. So that's not a distinguishable arrangement. So what happens with this repetition here is we have to do something a little bit different. Again, the word trip is 4 distinguishable elements, so it's 4 factorial, 4 times 3, 2 times 1. But if we have repeated elements, where they're not all unique, we have to divide by the number of elements of type 1 factorial, the number of elements of type 2 factorial, type 3 factorial, and on and on and on, no matter how many elements there could be. So if we were to do this formula up here, again, you have 4 letters, so 4 factorial, but there's 1 P, so you divide 1 factorial. There are 2 O's, so it'd be 2 factorial, and L, there's 1 element of type 3. So 3 different elements all multiplied together in the bottom there, using this formula down here. Well, the 4 factorial is 24. We saw that over here. 1 factorial is always 1, so you have a 1 and a 1 here. The 2 factorial is just 2 times 1, which is just 2. So we actually get half as many arrangements up here. And again, I'm not going to write those all out for you to save time, but this is the formula we need to use when we are doing permutations with repetition. So what does that look like in a bigger example? Well, if we look at the letters in the word Massachusetts, okay, you have what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 letters. So you start with, the 13 factorial on the top. Now, before in the formula, right, it tells you to write all the elements of type 1 factorial, type 2 factorial, type 3 factorial. Well, if there's just one element, like we saw up here, there's just 1 P, it's just a 1. Okay, so we don't need to worry about that. So really just write the elements that have repetition with a factorial on the bottom. So there's 1 M. All right, so we don't worry about it. There's 2 A's. Okay, so we actually have to write that down, 2 factorial. There are 1, 2, 3, 4 S's. All right, there is one C, so we ignore it. There's one H, so we ignore it. One U, so we ignore it. And then one E, but two T's, so we'd have 2 factorial again. Okay, so then when we're actually going to evaluate this, you have 13 factorial divided by biggest mistake students make, put parentheses. All right, if you just wrote it 2 factorial times 4 factorial times 2 factorial without the parentheses, you're going to get it wrong. So 2 factorial is just 2, because remember what factorial means. It's 2 times 1. So it'd just be 2 times 4 factorial times 2 factorial, which is 2. Again, so we end up with 64,864,800 different ways that you can write the combination of those letters that are unique. Okay, so how many different integers can be formed using all the digits of the number 253,225? Well, again, you've got 6 digits, so 6 factorial to start with. You've got 1, 2, 3 2's, so 3 factorial. You've got 2 5's, so 2 factorial, and then just the 1 3, so ignore the 3 there. And just for reference, 6 factorial divided by 3 factorial, 2 factorial, this doesn't equal 6 factorial in the bottom. Okay, that's not how it works. So again, you can just do 6 factorial divided by 3 factorial, which is just going to be 3 times 2 times 1, and 2 factorial, which again is just 2 times 1. But there are 60 different integers that we could write with those digits. Okay, so kind of an application of this would be something like this. All right, so the grid represents the streets of a city, and suppose Mr. Stampstead wants to run with the wind at his back, which is coming from the northwest, meaning it is going this way. The wind is blowing that way. Therefore, he can only run south or east, south being down, east being this way. How many routes can he take to get from point A to point B? Okay. The reason why this is in this section is if you consider each block a letter, then you form words here. So you form a bunch of words using just the letters S and E. Okay, so there needs to be some combination of S's and E's that are going to let him traverse this distance, right? Now he needs to go 1, 2, 3, 4 blocks south. He needs to go 1, 2, 3, 4, 5, 6 blocks east. So there are 4 S's and 6 E's in this supposed word. Now this is just one possible route that he could take, but he could also go south and then east. You could go all the way east and then south again. That's a different combination. But again, it's just these combinations of letters. So you see here there are 10 blocks that he needs to travel. So 10 factorial. 4 of those blocks are going south. 6 of those blocks are going east. So that would be how we would set this up. So again, just use your calculator. 10 factorial divided by 4 factorial and 6 factorial. So he has 210 different ways to run from A to B. Now this section was also called circular permutations. And you're going to see why in just a second. So a circular permutation, I've given us an example here. Suppose Tanner, Lindsay, Taryn, Kendra, and Maddie need to sit at a circular table. In how many unique ways can they do this? So, pardon my lovely drawing here, but let's say we have a lovely circular table where Tanner sits here, Lindsay sits here, Taryn sits here, Kendra is here, and Maddie is here. Okay, the reason why this is a little different is because if it's a circular table, it doesn't matter where Tanner sits. If he's sitting next to Lindsay and Maddie, and Kendra and Taryn are in their positions, it's the same. It doesn't matter the orientation of the circular table. Like if you guys are sitting in this order, then it doesn't matter where you guys are around the table, but the order in which you are sitting is the same. So essentially, just because Tanner's name was first, he's like the little keystone for this whole process here, right? It doesn't matter where he sits. He's ignored, kind of, which, I mean, we all know that. But anyway, so the person next to him is the first possible option. Okay, so if Tanner sits here, there are now 4 options to sit next to him on his left. And then after that, there are 3, and then 2, and then 1. So with a circular permutation, it's just 1 less than the total number of people sitting at the table. Factorial. That tells you how many permutations are available. So if there's 5 students, 5 people sitting there, it's just 4 factorial, which, as we've seen a couple times, is 24 different ways that you can sit.